So, we left off with a lengthy discussion about the heat balance equation. We are trying to understand how the body thermoregulates, not specifically in one direction or the other, but what are the elements that contribute to a change in temperature or to the need to regulate and change temperature. I always tend to go a little more in depth on this slide than I want to, because the next few slides are on these individual elements. It's not bad, because now that's just going to be review. We're going to touch on each of these again in turn to remind you of where we were when we left off in class on Tuesday. So, metabolism is the sum total of all processes that generate heat, that generate energy, that are used to accomplish work. And maybe you've seen something like this, and it's not our job in this class to go through the TCA cycle and reducing equivalents and glycolysis and fatty acid metabolism. But all of these things add to heat production during exercise, or even heat production at rest. It's just a lower amount of heat production at rest. And if we wanted to put numbers into that equation, it's pretty straightforward. Metabolism, we have a way to measure and calculate and assign a value to that factor. It's easy to calculate, especially at steady state. And I think you have experience with doing this with expired gas collections, where you measure RER and VO2, and you can calculate the caloric equivalent and how many calories were expended at that exercise. Very easy during steady state, because the rate that you consume oxygen is indicative to the rate that you are producing energy. Again, this really only pertains to steady state exercise, aerobic type exercise, where oxidative phosphorylation provides the majority of that energy. At steady state, if we can measure O2 consumption, which is easy, we can approximate ATP use or ATP production. We use those interchangeably. They're two different sides of the same coin. And so we're not doing that here, but you've probably seen a table like this before. In XPhys, I know one of you has seen it in clinical XPhys, but this is a table describing the mix of macronutrients and their energetic contribution. So RER ranges from 0.7 to 1, and that identifies the mix of fat and carbohydrate being used to produce energy. And the amount of energy per liter of O2 varies slightly, because you get slightly more with carbohydrate energy per liter of O2 than you do with fat. It's roughly 5 kilocalories per liter of O2. So if you can measure the amount of O2 consumed, pretty easy to calculate the number of calories expended. And if you have calories, you have kilojoules. If you have kilojoules, you have joules. And if you know how long that was, joules per second or watts, you can get a number for that equation. I like that kind of thinking. I'm a math person, I'm an equation person, but I'm not going to force that on you. We're not doing calculations. I'm just saying it's easy if you want to. Now, this next slide was sort of a rant that I had one year, and I considered removing it, but I think it's still worth mentioning briefly, especially since we highlighted, okay, it's easy to calculate metabolism if you're at steady state. If you're not at steady state, it's a little harder, right? VO2 varies. There's some recovery elements that you have to consider. So how do you measure metabolism for non-steady state exercise? O2 consumption is one way to think about it, but if it goes up and down, there's energy being expended in the valleys between those peaks if you're doing sprints or something else. That is hard to measure with this technique. A lot of individuals will turn their attention to lactate which I have a few issues with. Certainly this is increased in the blood during sprint type exercise. It's an indicator of really high rates of metabolic flux. But there's some problems with just using lactate to approximate metabolism. Lactate has nothing to do with, one, the phosphocreatine system, which I think you know. Doesn't indicate any energy coming from this system. Two, lactate in the muscle is not the same as lactate in the blood, so we would measure it in the blood circulating and try to approximate metabolism. But not all of it leaves the muscle. There's more in the muscle, and maybe the difference between these two is large. Lactate's used by other processes. It's not just produced and then escapes. Alanine aminotransferase is a reaction that connects glycolysis with amino acids. Doesn't matter about the detail, but lactate can be used there as well, which would skew our measurements. And then the idea of blood lactate not being accurate, we have to consider that if we put lactate into the blood, it doesn't just stay there. Tissues like the heart are really good at taking it up and using it for energy. So again, changing lactate values in the blood. So this isn't a good indicator of non-steady state metabolism. It's a good indicator that you are working at a high workload or are doing sprints or that non-steady state metabolism happened, but it's not a good indicator of how much was done. It's hard to calculate metabolism, a numerical value, using just lactate. What we could do, since we had the conversation about efficiency last class, what we could do is, if we know all of the work that was done, and we measured VO2 and we knew the aerobic work that was done, the difference between those would have to be non-steady state. Would have to be glycolytic, would have to be substrate level phosphorylation. We could figure out the difference. If we knew the endurance value by measuring VO2 and we knew the external work done, which is the subject of our next slide, and we assume that we're 20 to 30% efficient, we could figure it out. The difference between those numbers would allow us to figure it out. But it's not easy. So we often overlook calculating metabolism for repeated sprints or anything that's not steady state. And we'll maintain the status quo here. I just want you to be aware of that. So how might you calculate total work done? And this is another element in the heat balance equation. How do you figure out how much work was done? We went through a brief example last class, and it differs depending on the mode of exercise. So the background here is very similar, albeit more advanced, to what you're used to in West Street, the kind of bikes that you'll see in West Street. And this mode of exercise has a specific equation to calculate work done, which we're showing you here. The simplified version, RPM times the resistance, which we talked about in class. But this differs from a treadmill. If you were to run on the treadmill, it's not as easy to calculate work done. You need mass of the person because it's a weight-bearing exercise. Gravity is affecting the weight of that person or the amount of work that you're doing, so we have to correct for gravity, negative 9.8 meters per second squared. How quickly you're running on the belt, and then the grade of the treadmill. A much more involved equation, but we can still get total work done if we wanted to. Now we're not going to do this, but it's possible. Also keep in mind, I tried to highlight this last class, that this work being done essentially takes energy from the metabolic energy being produced. Takes energy from the metabolic factor in that equation. It's work that went towards, it's energy that went towards work and not towards heat. Therefore, work is always negative. It always subtracts from the heat balance equation. We invested energy in this work. We didn't invest that energy in heat. And if you were rowing, there'd be a different equation. If you were doing stepping exercise, there's a different equation. If you were playing hockey or soccer, there's no equation. We haven't modeled hockey or soccer yet because it's very difficult to model that, especially considering that it's not regular, repetitive exercise. A lot of other factors go into how much energy you expend during hockey or soccer, for instance. Radiation we talked about as the exchange of electromagnetic waves. Most objects, if they have some amount of heat stored in them, will emit these waves. They'll be emitted from one object and absorbed by another, depending on which has more. Always flows according to a gradient. Specifically, we're concerned with solar radiation, especially if we're exercising outside, and here it's not a problem. These fluorescent lights don't give off solar radiation, I think, which is good. They're not grow lights. But outside, there is a lot to deal with. If we have a lot of skin exposed, we absorb nearly all of the radiation that we encounter. That's the job of melanin, to absorb radiation, prevent the cells in the skin from being damaged, from DNA mutating, and from you developing skin cancer. So we absorb nearly all of that radiation. And it's not easy to figure out how much energy was imparted by that radiation. Clearly, these photons travel quickly, 300 million meters per second. And so consider what we discussed as heat. Heat is just how quickly molecules are moving. Well, if I have something coming in at that incredible velocity, it can impart a fair amount of energy to the skin, to the body. It can add a lot of heat. And it depends on a daily basis, especially here where our weather patterns are so variable, the amount of radiation we're exposed to can vary pretty drastically. So this is a trace showing total amount of solar radiation collected over the course of a normal day, from sunrise to sunset. Top panel is a clear, cloudless day. Bottom panel is a typical, partly overcast, mostly cloudy day. And so we're registering a progressive increase to a peak of about 1,000 watts per meter squared. 1,000 watts of energy per meter squared. A little bit bigger than the size of this desk, maybe two of these desks. 1,000 watts of energy per meter squared. And of course, variable depending on cloud exposure on a cloudy day. Even if you could measure this accurately, what does it mean? Does this matter? High velocities for photons, lots of energy from solar radiation, but what does it actually do? Well, in a stepwise exploration of, specifically, rates of solar radiation, we're looking here at the exercise time to exhaustion at 70% of VO2 max. No radiation, you go about 45 minutes in the heat. 800 watts per meter squared, which is below the peak that we saw on that last slide. It's cut in half, 22-ish minutes to voluntary exhaustion. So solar radiation, here we're only changing solar radiation. It can have a fairly large impact on our ability to perform, to do work. Now notice these are healthy college-age men and women in the heat. It might be different if it's a cooler environment or more or less humid. The point here is to get across that there is this stepwise progressive type relationship. Wind speed would affect this as well. So radiation can have a large impact measuring it is somewhat difficult, and we're not going to concern ourselves with that so much. Conduction and convection we talked about together. We know conduction is the heat transfer between media, two media that are in contact. And so a really nice example, what we think of normally are two solid media. This is a good example in the backdrop here, or your hand and the desk, your hand and an ice cube. Heat always flows from high to low. Just like anything else in physiology, follows the gradients. High O2 to low O2, high pressure to low pressure, high concentration to low concentration, high energy to low energy. Now we'll add some context to this idea. We've explored the idea of me imparting heat onto a cold desk. That is conduction. And that is what I would call an example of conduction that occurs outside the body. It's something external to me. But conduction also occurs inside the body, between the muscle and the blood. The muscle generates heat, and it makes the blood hot. The blood circulates. If the blood's hot, it makes other tissues hot. Eventually, your whole body warms up. All of that is due to the movement of heat between those compartments. Luckily, those compartments in the body don't change. If we were to model them and invest that time and effort, we could get a good sense of how readily heat moves between the blood and fat, or between the blood and muscle, or between the blood and the liver or the brain. But outside of the body, some things will readily conduct heat more easily. So metal, cold metal sitting outside, stings if you touch it right now. It rapidly sucks any heat in your fingertips touching that metal. Water has a high capacity to act as a heat sink. All because the molecules are really close together. Some things are not good conductors. Air. Molecules are spaced apart. Not as easy to conduct heat into the air. Non-metals, and really what I mean by that, things like plastic, rubber, other solids, and or fat tissue, all good insulators. And so you can appreciate that conduction, even if we could model it in a person, the total sum of conduction might vary depending on amount of muscle, amount of fat. It varies in the real world depending on where you're running or if you choose to swim. Highly variable. Convection is the next level of conduction. And we talked about the renewal of that media. You can't renew solids, but you can renew liquids and gases. So if heat is transported by a stream of molecules into a media, the first step of convection is actually not convection. The first step of convection is technically conduction. So imagine sitting in a nice cold pond. It's still. We are imparting heat from our body into the immediate layer surrounding us, and that fluid warms. That action is not convection. That action is conduction. But as that water warms, it's going to move differently in relation to the cold water surrounding it. It'll heat, it'll expand, it'll rise. And if it rises, it needs to be replaced. That area is immediately replaced by other colder water. And the process is repeated. Not to mention the fact that maybe there's a current which doesn't rely on the passive heating and movement or rising of that fluid. Maybe the current pushes it out of the way and the process repeats. Now I think this is the easiest example to imagine, but the reverse can happen. It's not often that we sit in really hot water or sit around in really hot air, unless you're Finnish. Anyone have a sauna recently? Really hot, humid air, dumping water on the rocks, get a blast of steam. My family lives in Thunder Bay, which has the largest, I think, per capita Finnish population outside of Finland, so everyone has saunas. We grew up with saunas on the dock. You'd run and jump into the water. It's an oppressive kind of heat. It's not common, but you can gain heat, certainly, through these exact same processes. You're in hot springs or in the hot air. The same process occurs following the gradient, high energy to low energy. It all depends on what the two heat loads are in those media. So I think we have a good sense of what conduction and convection are and specifically how they differ. These we alluded to are referred to as dry heat. What are some things that will change how much dry heat impacts heat balance? The obvious first example is a change in temperature. Temperature being a measure of the heat within those two media. If there is more heat, if there is a larger temperature, the gradient will dictate whether heat flows in or out of the body. Surface area. If you have a larger surface area, you have a greater opportunity to exchange heat. It's dictated by the gradient, but having a larger body surface area, being a larger individual, dictates that you have more opportunity to exchange heat. But what you might do as a larger individual, knowing this, maybe you cover up more. The exposed surface area is where heat exchange occurs most readily. It's not to say that if you're wearing clothing, heat exchange won't occur. It might just be impeded. And we'll talk about this maybe. I have it in this section, but I might take it out. We'll talk about the effect of clothing in brief. We don't ever touch back on it, but it is somewhat interesting to consider. Exposed surface area influences how much dry heat loss can occur. The type of environment that you're in, are you in contact with water or air, or are you touching solid things? Are the oars on your rowboat really cold? Are they made of metal? Are they made of wood? Are there specific places where heat loss is accentuated? Rubber versus metal versus wood is an example of the density of some media that might be in contact with you. Or are you running outside in the air, or are you swimming in a cold lake? The density of the medium affects dry heat loss. It might seem a bit counterintuitive to think of swimming as being a factor affecting dry heat loss, but you understand why I can put this in that example, right? Dry heat loss being conduction and convection, wet heat loss being evaporation. So sitting in a cold bath is still affecting dry components of heat loss. Okay, what else can affect dry heat loss? The list seems to just go on and on. How quickly the medium is renewed. We've talked about that. One that we haven't talked about, which is somewhat interesting, is a change in altitude, which is just another example for varying density of the medium. I think it's already pretty straightforward and you have a good grasp on if you're in liquid versus air, dry heat loss is affected somewhat differently. Altitude is an example of that principle. So imagine sitting here right now and there's a column. You have a crown or something that you're wearing that extends all the way up to space. From here at sea level, there's air in that column until there's no air in space. And all of that air in that column, it's imperceptible, but it's weighing on you. Those air molecules have a weight. And so everything right above your head is weighing on you specifically. If you're here, there are a lot of air molecules, so there's more weight than if you were at a higher altitude. Go halfway to space, you have half the air pressing down on your head. There's much less air, much less pressure. It's less dense, and that's what I'm trying to get at here. Same principle as water versus air. The turbulence of the circulating medium can affect dry heat loss as well. Does everyone know what laminar flow is off the top of your head? So when you were studying blood flow in vessels, maybe you're talking about it during your blood pressure section of A&P, but blood generally flows in vessels fastest in the center and then progressively slower as you move out, right? Because the walls of the vessel are always trying to slow the blood down. But in the middle, there's no opposition. So you get this parabolic flow. It's fast in the middle, slow around the outside. We call that laminar flow. That is really good at exchanging heat. It's uniform. Turbulent flow is not. Turbulent flow has some parts of the media are warm, some are cold. There's no uniform distribution across the surface. It's not easy for heat to be exchanged through a turbulent medium. And you can probably come up with many more examples. That might be a good exercise for you. And while I've talked mostly, I've been general in my descriptions, the direction is affected by the gradient. If you are in cold, all of these examples, you will lose heat. The opposite is true. If the medium outside is warm, you will gain heat. The effects are equal and opposite depending on the gradient. So those are factors affecting dry heat loss. We didn't talk about the factors affecting metabolism or work because really it's how much you choose to do. You can exercise harder or more easily, longer or shorter. These are things that are not necessarily inside your control. Some things are like clothing or when you choose to exercise, but these are intangible factors that affect dry heat loss. The last example, evaporation and or wet heat loss. Fantastic method of dissipating heat to the environment. If we can evaporate 1 liter of sweat, which is typically what happens for most individuals in an hour, you sweat a liter, it removes 2.4 million joules. 2.4 million joules. Imagine if you did this in a second. That's 2.4 million watts of energy lost. A joule per second is a watt. Fantastic capacity to remove heat from the body. But this is affected by whether or not the air around you can accept that water vapor. Whether or not the air is dry enough to allow evaporation. And what I'm specifically referring to is this idea of water vapor pressure. And we don't often think about water vapor or how saturated the air is. The closest we come is in thinking about relative humidity. 98% relative humidity in the summer. We know that's oppressive. We know that feels really hot. But we haven't ever really thought about what that means. That humidity describes how much water vapor is already in the air, and therefore how much is left, how much capacity there is for that air to accept new water vapor. Let me show you what I mean. So this is a trace of normal ambient air, or I guess normal air across a range of temperatures, 0 degrees to 50 degrees. And this solid line shows how much water vapor air at that temperature can hold. At low temperatures, air cannot hold very much water vapor. There's very little capacity to evaporate water and load the air with vapor. But at high temperatures, we have a fairly large capacity. Air can accept a lot of water vapor. So we can compare two scenarios. Think about what these might feel like. 30 degrees Celsius, 70% relative humidity. Okay, that's hot. That's not the worst summer day that we've had. We've had 30 to 35, 95% humidity as early as last year. I remember that being here, thinking, this sucks. But that's hot. We know what that feels like. We might not know exactly what 40 degrees Celsius and 20% humidity feel like. But just from first principles, we know 40 is higher than 30, and this sounds hot. This is hotter than body temperature. So clearly, it's going to be harder to thermoregulate in this second environment. Let's consider evaporation as a way to lose heat. What I want you to look at is not the arrows, but the space left after the arrows. So in this first environment, it's very humid, and we have this small capacity to add more water vapor to the surrounding air. It's hard to evaporate sweat efficiently and lose heat in this environment. Contrast that to a nice dry desert. Look at how much capacity we have to evaporate sweat from the body and lose heat to the surroundings. Even though it's higher than body temperature, we can still thermoregulate efficiently, and perhaps even more so than in this lower temperature first environment. We have a great capacity to evaporate sweat into the surrounding air. Now, if this were 40 degrees and 70%, it would certainly be worse. But because the relative humidity is different, we have a greater capacity to evaporate sweat into the surrounding air. One way that we try to get around using these two numbers is the humidex. We'll talk about that briefly at the end. If you compiled both of these numbers in these two scenarios into one humidex value, you get the feels like number. And this first example feels like 36 degrees. The second one feels like 40 degrees. So it feels similar despite there being a fairly large difference in the actual environment. More on that and wind chill coming up. Let me just make one mention of respiratory evaporation because the slide is in here and it's in your slide set, and we mentioned it last class, and then we'll take a quick break. So this idea of heat exchange via airways is not something we often concern ourselves with, but in an instance where we have very dry air and we're exercising really hard, ventilation can get quite high. And 100 liters per minute, it's high, but during a VO2 max test, you might see 150, 180 liters of air per minute. There's a lot of air moving in and out. If that air is dry, we have a very large capacity to lose fluid and lose heat via this medium. So who's done a VO2 max test here, by the way? Small compliment over there. And you had the mouthpiece in the whole time. And think back, did it start to feel dry? Very dry. Your mouth started to feel dry. It's always open. You're only breathing through your mouth. Your nose is closed. And you just want to drink water. Eventually, at those high workloads, the workload distracts you. The second last and the last workload, you're thinking about other things. You're not thinking about dry airways. But it's that really dry, lip-smacking feeling that I'm describing here. With high respiration rates, we have a large capacity to lose fluid and lose heat. And that's just because we have to heat the air that comes in, we have to humidify the air that comes in. If the air is already hot and humid, then there isn't a large difference outside versus inside the lungs. But if it's dry and if it's cold, then heat loss through this pathway is large. So in a cold, dry environment. And one really interesting use for this phenomenon is in rewarming. So individuals that have been lost at sea, immersed in cold water, subject to hypothermia, this is one way that is a potential avenue for rewarming, other than packing them in a nice insulated blanket, one of those Reflectix blankets, because they might have a really low core temperature and you're not trapping very much heat. If you can instead infuse really warm air, have them breathe really warm air, this is one possible use for this in warming them from the inside out. Not something we'll study at length, but just a way to leverage this phenomenon for our benefit. So let's take a quick break. Go grab a coffee, head to the washroom, run up and down the stairs. It's early. Let's get the blood moving, move around. Talk to your neighbors, and we'll reconvene, start back up at 9. So that's 7 minutes. Sound good? All right.